Hello, and thank you for attending my talk. My name is Rahul Chandan, and I'm a fifth-year PhD student at the University of California, Santa Barbara. Today, I will be presenting you some exciting results about concessions in competitive interaction. This is joint work with Keith Paarporn, Mahnoosh Alizadeh, and Jason Marden from UC Santa Barbara, and Dan Kovenock from Chapman University. When considering the Merriam-Webster definition of concessions, we immediately observe that concessions are often associated with giving things up or with defeat. For example, concessions in biology can represent lizards, octopi, and other animals sacrificing their limbs or other body parts to save the rest of their bodies when cornered by predators. In economics, we know of many examples of companies that had to abandon competitive market segments in order to save the rest of their business. A prime example is that of Blockbuster video stores that closed down after losing all their market share to streaming services such as Netflix. Finally, in military history, we know of many examples where leaders chose to surrender to their opponents in order to save their troops, especially when victory was hopeless. We are all familiar, for example, with the surrender of the Japanese in World War II in the face of complete annihilation by the United States. The main takeaway from these examples is that concessions are commonly considered as acts made in desperation at the last possible moment in order to mitigate losses. In this respect, we pursue a fairly non-intuitive line of questioning. Would a competitor ever make a concession early on to seek a strategic advantage and win more in the competition? In this talk, I will highlight how concessions are indeed a valid strategic option in competitive settings, in the sense that competitors can often benefit from making concessions. This challenges the common intuition on concessions that they should only be made at the time of imminent defeat in order to mitigate losses. We consider this question under the framework of the general Lotto game, which is a commonly studied model for decision-making in competitive interaction. In a general Lotto game, there are two competitors, A and B, who may represent either firms or armies or animals or whatnot. Each of the competitors has a fixed amount of assets, which may be money or troops. Finally, there are end fronts that have associated non-negative values, which can represent markets or battlefields. In the figure on the right, observe that A is the stronger competitor with 5 assets, whereas B is weaker with only 3 assets, and that they're competing over end fronts with values V1 through Vn. The primary question in the literature on general Lotto games is, how do the competitors allocate their assets to the various fronts? This answer is most often posed in terms of payoff guarantees, where the competitors are modeled to be in direct competition. In order to guarantee some payoff, observe that B must make her allocation knowing that A's response will seek to minimize B's payoff in the box in the slide. As you can see, B attempts to maximize her payoff through her choice of allocation, and furthermore, B will assume that A observes this allocation strategy and responds in order to minimize B's payoff. This type of optimization is known as a maximin optimization. Formalizing the expression a tiny bit, we see that the optimization is over 2 cumulative distribution functions, FA and FB, on Rn. In the general Lotto game, the competitors' allocation strategies are randomized or mixed and are represented by the functions FA and FB. These strategies represent the probabilities that the competitors use specific allocations, where an allocation is simply a vector on Rn. Each competitor's payoff is the cumulative value of fronts she wins in expectation over the mixed strategies, where a front is won by the competitor who allocates more budget to that front. Observe in the box that we've replaced B's payoff with this expectation over the functions FB and FA, where the sum simply counts all of the battlefield or front values where B has allocated more of her budget to that front than A. Finally, competitor strategies must satisfy their budgets and expectation. And here we've replaced the expression, we've replaced the statement with this expression. It's important to note that the general lotto game is a constant sum game, since the competitor's payoffs will always add up to the cumulative value of the fronts. This is important as it implies that the competitor's payoffs in equilibrium are unique by the von Neumann minimax theorem. The equilibrium payoffs in the general lotto game are well known and were characterized more than 10 years ago. As mentioned, we pursue a parallel test under the general lotto framework and ask whether either of two types of concessions can provide benefits to a competitor. We assume that the concessions will be made prior to the competitive interaction and that they become public knowledge immediately after they are made. The first concession type that we consider are asset sacrifices, where a competitor discards a portion of her assets. Observe in the figure on the right that now B's completely sacrificed a full unit of her assets, and that her remaining budget is now 2 as a result. The other type of concession that we consider is that of front abandonment. Observe that now in the figure on the right that B still has a budget of 3, but now she abandons front N, and that the value of front N is immediately awarded to competitor A. As one might have expected, we show that both these types of concession cannot benefit the competitors in the general lotto game. Next, in order to study if this intuition generalizes further, we consider a slightly more complex setting, which we term the 3-player general lotto game. In this game, competitor A now simultaneously competes in independent general lotto games with competitors B and C. The 3 competitors still have fixed amount of assets, and the general lotto games are over disjoint sets of fronts, as shown in the figure on the right. This game has 2 steps. First, A allocates her assets to the 2 general lotto games, as we've represented with the variables XAB and XAC in the figure. Afterwards, A allocates her assets, the 2 general lotto games are played. It is assumed that A's allocation in the first step becomes common knowledge before step 2. Once again, the primary question in this setting is how do the competitors allocate their assets to the various fronts? Since B and C have fixed amount of assets and only play in their respective general lotto games in step 2, we only need to derive A's allocation strategy in step 1, since the equilibrium payoffs in the general lotto game are known. The problem of deriving A's optimal allocation strategy was answered by Kovenock and Robertson in their 2012 paper. As we did with the general lotto game, we pivot to a parallel line of questioning, where we investigate whether concessions can help in the 3-player general lotto game. This is done by including a preliminary step 0, in which player B makes a concession. At the end of each of these each of the steps of the three-player general lotto game with concessions, the actions that players have made become common knowledge. This means that A's allocation strategy in step 1 of the game will be in response to B's concession, and that this is the mechanism by which B can change the outcome of the game. With this in mind, we first ask whether B benefits from sacrificing her assets. Once again, we depict this in the figure on the right, where B now has a remaining budget of XB minus X. Once more, as we already expected, we showed that sacrificing assets cannot benefit B even in the three-player general lotto game. We then consider whether B can benefit from abandoning a front. And here, again, in the figure on the right, we depict this by B opting not to send any budget to front 1, and that front 1 is immediately awarded to competitor A. In this case, perhaps surprisingly, we show that abandoning a front can often benefit B in the three-player general lotto game. This means that in general, concessions do represent a strategic mechanism in competitive interaction, which contradicts the expectations that we had from the previous results. Recall that in the general lotto game, which represents a 1 versus 1 setting, we show that concessions cannot benefit the competitors, and we represent this fact by the blank plot on the right. However, in contrast, we showed that in the three-player general lotto game, which is a 2 versus 1 setting, there are many scenarios where B can benefit from concessions. Consider the setting depicted on the left. Here, competitors A and B are engaged in a general lotto game over fronts with a cumulative value of 3, while competitors A and C are simultaneously engaged in a general lotto game over fronts with a cumulative value of 2. Moreover, we have fixed C's budget to be precisely 1, while we will vary the budgets of A and B. The blue region in the plot on the bottom right coincides with budgets of competitors A and B, where B has a beneficial concession for the specific setting depicted on the left. These benefits are all achieved by abandoning a front. Our results suggest that a third party is needed for a competitor to benefit from concessions, and that the beneficial concessions can exist under a variety of game parameterization. A pertinent follow-up question is, how much do concessions really benefit a competitor? For the same setting that we considered previously, we plot the percent improvement in B's expected payoff after the concession. In the plot, we show this percent improvement when B's budget is either fixed to 0.5 or 1.25, and A's budget is varied from 0 to 2.5. Note the corresponding lines in the plot in the bottom right. Notably, in this simple example, we observe that B's payoff can be improved by more than 50% by simply making a concession. Colloquially, concessions are often associated with last resort measures, taken to mitigate losses in the face of defeat, as we observed from the examples in the introductory slide. However, our results demonstrate that perhaps surprisingly, competitors can often use concessions to their benefit. In our work, we considered 2 types of concession: asset sacrifices and front abandonment, and saw that abandoning a front can benefit a competitor when a third party is present. In future work, we are interested in answering the following questions. Do our results on beneficial concessions generalize to larger classes of contest models, such as Tulloch contests? and to broader interaction graphs with more competitors and more fronts. And also, if more than one competitor can concede at the same time, what are the emergent stable outcomes or equilibria of the corresponding game? Thank you for your attention. At this time, I would like to take any questions.